Hello Year 12, welcome to the next video here in our series in finance. Well, our finance is over, pretty much. We are now looking at some other things, and we're pretty much leaving the APs and GPs behind as well. We're looking at rates of change here, and we're going to do this with calculus. How wonderful. Back to calculus. Now, if I have some quantity Q that varies as a function of time, that is, Q is equal to some function of time, then the instantaneous rate of change of Q at some point t is dq by dt. Alright, that rate is going to be equal to or equivalent to the gradient of the tangent to the graph of that curve. Now, let's have a look and see how we can apply these things. I've got a question about cockroaches. How wonderful. Now, if I have a quick look at this, I see that this is a quadratic function that has a negative coefficient of the squared term. So this is concave down, means it's got a maximum somewhere. It means the population, probably between these bounds, is going to go up and back down again. We will see how that happens. Now, here's my function. I need to differentiate it. That's all it says to begin with. Differentiate that. So dp by dt is equal to 6 minus 2t. Just like that. That's how the population is changing. Now, find the cockroach population on the 1st of January. So that's where, at t is equal to 0, my population is equal to 7 plus 6 by 0 minus 0 squared equals 7 million crawlies. Bugs. That'll do. Bugs. Easy to write. Also, dp by dt at t equals 0 is 6 minus 2t is 6 million. Right, that's increasing because it's positive. Whew, look at that. There's 7 million and it's increasing by 6 million. There we go. At what point in time did the population stop increasing? Right. So it's increasing to begin with. We can see it. To begin with, it's increasing at a rate of 6 million cockroaches per month. 6 million cockroaches. But at some stage, that's going to stop. So that's when, if dp by dt is equal to 0, neither going up nor going down, it is steady. When did that occur? Well, dp by dt equals 0, and it's also equal to 6 minus 2t. Therefore, t is equal to 3, which is 1st of April. April Fools. 1st of April, right? That is when the population stops increasing. What is the population at that time? Well, my population is described as 7 plus 6 lots of 3 minus 3 squared. So this 18 minus 9 is 16 million cockroaches. Land prawns. 16 million cockroaches. Now, because the population was going up until this point, and then it is going down, this is going to be the high point of the population. There will never be more than 16 million populations according to our model. That's nice. So on the 1st of April, we hit a maximum of 16 million cockroaches. The population from that point onwards went down. When did it fall to 0? Well, let's say that p equals 0, which is equal to 7 plus 6t minus t squared. So we could also say that t squared is not equal to t squared minus 6t minus 7 equals 0. T minus 7 t plus 1 equals 0. I'm just going to say t equals 7 months. I'm going to say that, which is August, I think. Because typically when we're talking about these applications, we might rule out things that are negative periods of time. That would imply that on the 1st of December, the population was 0 and it had climbed, but nonetheless, it fell to 0, that's the sort of part of speech there, suggests when did it fall? It suggests that it wasn't falling on the 1st of December at t equals -1. It was rising, right? You can hardly rise to 0. We didn't have a negative population. But anyway, it fell to 0 on the 1st of August. All good? There we go. So that is differentiating to work with rates of change. Of course, we can integrate as well. One thing that I will tell you to be careful of, one, make sure there's power in your battery and that you save things and back it up. It's a long story. But no, seriously, be careful when you are integrating. Don't forget that constant of integration. Now, press pause if you like, read through this question carefully, but we have some function here. In fact, what I have is the differential. I have the derivative of some function. We have this thing here. When does it stop flowing? Well, that is when dv by dt equals 0. Negative 1500 plus 30t. Therefore, 30t equals 1500 and t is equal to 50 seconds. Yep. Water stops flowing after 50 seconds. Now I want to find the volume of the water tank time V. Well, my volume is going to be the integral of this is negative 1500t plus 15t squared plus a constant. Well, I know that at t equals 0, V equals 40,000. Okay, tank contains 40,000 litres of water. T is the time after the valve is open. So we know those things. Therefore, I can say 40,000 is equal to 0 plus 0 plus C. Therefore, my volume is equal to, I'm going to say it's 40,000 minus 1,500t plus 15t squared. There we go. Notice how we had a constant of integration there and we found some point there we could substitute in to pin that down. Okay. Now we've got a function that describes the volume of the tank. How much water drains from the tank before the valve closes? Well, there's probably a few things we could look at here, but I'm going to look at the volume of the tank when t equals 50. Okay, because I know the water stops flowing at 50, that's when the tank closes. So, my volume at 50 is equal to 40,000 minus 1,500 times 50 plus 15 times 50 squared. Thank you, calculator. All clear. 40,000. Hey. Whoa, what's going on there? Oh, that's not what's going on. Oh, I'm going to say, oh, geez, hang on. Right, I'm back. 40,000 minus 1,500 times 50 equals plus 15 times 50 squared equals 2,500. So, the volume of my tank after 50 seconds equals 2,500 litres. But, is that the answer that I'm looking for? Everything's gone belly up here. Is that the answer I'm looking for? I don't think so. Find the volume of water in the tank at time V. There we go. Volume of water in my tank is 2,500. Like that. Oh, sorry. Why did I write that up here? Because those things went all wonky, isn't it? Alright, write those things out. Now, no, how much water drains from the tank? So we worked that is equal to 2,500. How much water has drained from the tank? Well, we started with 40,000. 40,000. And I'm left with 2,500. So that means that 37,500 litres have drained. Okay, rates. There's a few other things that go with this topic, some stuff with interpreting graphs and so on, but I think we've seen a lot of those things before, and we'll go through it in class. Okay, thanks guys, I'll see you there.